session of the Neurosymbolic Programming tutorial. So this is session 3, and basically we're just going to do a really brief survey of some advanced topics, and then we'll conclude with our final hands-on exercise, which will be a tutorial on using neural relaxations for informed search for program synthesis. And so here is the outline of the session. So if we recall, the hardest part about program synthesis relative to classic deep learning is searching over program structures or program architectures. In general, you can think of the logical or symbolic structure of the programs as forming this space of possible architectures, which in general is discrete, and we need, and most importantly, combinatorial, and we need to figure out a way to search over this combinatorial space when synthesizing programs. What we saw in detail at the end of the second half of session 2, which will be the main topic of the working session for this session, is using neural relaxations as an admissible heuristic for graph search algorithms such as A-star search, once you cast program synthesis, or at least the architecture part of it, program synthesis, in the language of graph search. And the basic idea is that if you have a partial program that you haven't completed yet, you just complete it with a large neural network, which is then fully executable. You fit the parameters of this neural network, you measure its loss, and it becomes a lower bound on the best possible loss you can achieve with any completion of this partial program. And so the intuition is that if a large neural network cannot fit this hole, then no neurosymbolic completion can, and you can prune this branch of the search space. And that's the entire intuition behind all admissible heuristic-based informed search algorithms. And in this particular case, we're just using a neural network as the way to approximate or implement this heuristic. I'm going to briefly talk about another family of methods, and you've seen these methods being talked about in various talks throughout this summer school. I'm just going to give a really, really simplified version of it, just so we can sort of talk about the bare bones version of it, which is learning to search. Some people call this neural-guided search. And so the basic idea is that we're going to learn which branches learn to predict which branches of the search space are more desirable or less desirable. So for instance, you know, if we're at this part of the search space where we're considering whether how to branch on this partial program G star and fill it with more structure, then we have a neural net that takes as input the context of the task, the context of where we are in the partial program, and then just predicts a desirability score over the branches in the way that we can complete this program. And then we pick one, either using sampling or just the most likely prediction, and we greedily top down just pick one way to keep filling the program until we reach a complete program, and we never backtrack. Backtracking is something that we do in A-star search. Here we just greedily just depth first, never backtrack, using the priorities generated by this neural network. Another popular line of work is to do beam search, which is to keep track of the top K most likely sequences. You can think of this as top K greedy rather than top 1 greedy. Other methods include things like sampling, which people have talked about in different talks in this summer school. And so these are all predicated on the fact that we have this neural network that has been trained to be able to predict these desirability scores, and we use them to very simple search heuristics. So why might this work? So the reason why this would work is that this neural network that is guiding the search process is trained on many related synthesis tasks. You have a data bank of tasks, of programming tasks or program synthesis tasks that are related to each other somehow. And you've learned a neural network that somehow learned the implicit structure or the implicit patterns that is useful for all of these tasks. So unlike the neural relaxations that we talked about last session, which is only on one task. And therefore, for neural relaxations, we require backtracking because it's only on one task. And so because in this neural-guided search or learning to search, the neural network has been trained on many tasks, it somehow has encoded more information about this whole collection of tasks, and you can just greedily follow the neural network's predictions to generate a full program without any backtracking. And this is very similar to language models where a neural network can complete a prompt by just forward sampling. So here's the basic setup. You have a task, and a task is, in this simple case, it can get more complicated. In the simple case, you have a ground truth program, And then you have a bunch of input-output pairs generated by this program. So for this input, the program generated this output. So this is the training set, the set of related tasks, and you have multiple of these, hundreds, maybe thousands. For example, you can generate programs from and inputs randomly and then compute the outputs. That's what some people do. And the neural net basically learns to map this input-output pair to the target program. That's what neural-guided search does, or learning to search does. And in particular, most of the time, it's predicting one token at a time. So that's why it's doing this that's equivalent to this forward greedy search. And so this is basically, in some sense, a form of sequence prediction, which arises in things like question answering, translation, and complete text completion, where the input is a sequence and the output is a sequence. And you just need the appropriate training set for this. And so, you've seen many examples of neural architectures that could do sequence completion. This is just sort of a cartoon summary, that simplification of it, where you typically you encode your input sequence, which is variable length, so it can be length 2 or length 100. You encode it into some sort of fixed length embedding, which is essentially a fixed length feature vector that represents some encoding of this variable length input, and then you decode it into this variable length output sequence, which is in our case a program. And then there are neural architectures of choice that can realize this type of input-output encoding decoding, including things like recurrent neural networks, such as LSTMs, and various forms of transformers, which are based on this attention mechanism. Okay, so one example of this that people have talked about in different talks is robust fill, which does exactly this. You have this family of programs and ground truth programs and input-output examples. You train a neural network to guide the search, and then you just output the program one token at a time. Oops. I think in the interest of time, I'll skip this. This is just pulled from their paper. This is just one example where you have lists of names and lists of names with commas, and then list of names with commas, and then you synthesize a program that that adds commas. And so just a comparison summary. In terms of learning to search, at the end of the day, when you're doing synthesis, you have a very simple search procedure, relatively speaking. You just sort of do greedy or beam search, and it's typically very fast. For things like neural relaxations, you're using more informed search algorithms, which do some backtracking and can be slower. For learning to search, it requires having a large training set for which you can pre-train this neural network to guide your search process at synthesis time. For neural relaxations and A-star search type methods, you don't need pre-training, although it can help. For learning to search, you need many tasks with ground truth programs, typically, in order to be able to do this task. And you've seen examples of this in other talks. For neural relaxations, you only need your one task. You don't need anything else. And obviously, you can imagine more advanced methods that can enjoy the benefits of both of these with different amounts of training resources available.
Okay, so in this summer school, the name DreamCoder has come up several times. So we thought that we would just talk about the DreamCoder approach to library learning just a little bit. So specifically, the problem is that you are starting with a bare bones initial language in which you have, let's say, some combinators like if then else's, cons over list, map, fold, and so on. And now let's say that you're given a bunch of more complex tasks. So what you'd like to do is to come up with reusable ways in which these simple initial primitives can be combined, and then extract those motifs from the programs that are solving these tasks, and then add them to the library. So just to make this concrete, let's imagine that you have this sample problem, which is sort list. So you're given a few examples for this problem, and then you are starting with this initial bare bones language. So let's say that as you are trying to synthesize this a program in that initial language for this task, you come up with this concept, which is, so this is a subprogram that is made up of these, some of these initial primitives. And what this is doing is that it's filtering a list. And then in the process of doing this kind of synthesis for a sorting program, you might come up with a function that does maximum. And note that this concept 13, this is actually using this concept 4 as a library module. So what you would like to do is to, out of this process, come up with filter as an additional primitive and max as an additional primitive. And then, going even further, of other programs, subprograms you can construct. So there is this program for finding nth largest element. And this is something that uses concept 13, which is maximum, and concept 4, which is filter. And then all of this together will help you construct a program for the final task, which is in this case sorting. And if you're not deeply familiar with functional programming, don't worry, that's a program in a higher order functional language for sorting. And what this is doing over here is that it's using the idea of, or it's using the subroutine of finding the nth largest element in a list. So it's just applying a map to the original, so to a list that is 1 to n, and it's just constructing, filling the ith element with the nth largest element in the original list. So if I wanted to write this program for sorting in terms of the initial primitives, you'd get something like this, which is massive. But the idea here is that as you are doing this synthesis, you are extracting these sorts of reusable primitives. And so the next time you have to do something related to lists, you'll be able to use those functions, and your programs are not going to look like this, but more like what you see on the right-hand side. And we'll also note that this process, because of the synthesis methods, the program synthesis methods that are being used, it's actually relatively fast. If you wanted to just brute force this to search for these library routines, that would really take forever. So then the question is, how does this actually work? The overall idea is broken down into these 2 sub-ideas. So one of them is that you have a phase where you are solving problems, such as the sort problem that we saw earlier, by writing programs. And then looking at those programs, you are improving the library that you currently have. So while writing the program, you can use the current library, but using that program, you can improve the library. You can add additional components. And then the process of program synthesis is being driven by a neural net. It's neural guided synthesis. And so that neural recognition model, or the neural guide for the synthesis process, that is also being improved. And so you can think of this as a cognitive process where you are awake part of the time, where you're solving these programming problems by writing code. And then while you're sleeping, you are improving your background knowledge about the world. And there is the abstraction phase, and there's this dream phase where the neural network is getting better for guiding synthesis. So what Kevin Ellis and Armando and Josh Tannenbaum and co-authors, what they showed is that this general idea can be applied to do some very exciting things, starting from a really basic lambda calculus, which is essentially the simplest functional programming language that exists. You can come up with reusable primitives for a whole bunch of different kinds of tasks, like list processing and text editing and regex and symbolic regression, physical laws, graphics, and so on and so forth. So just to give you a very high-level overview of these 3 different stages that we talked about, and I can't go into too much detail. You'll have to read the paper. But this is the first phase where you are awake, you're writing programs. So you have a library, you have a task, or in general, you have a set of tasks, but you are sampling a task. And then you are using the synthesis process, the neurally guided search process, to come up with programs. Okay, and then there is an equation for this that you can see in the paper in more detail. But basically what this is trying to do is to come up with a program that solves these tasks optimally. right? Given the priors that are there in the form of the library and this neural model. And then in the dream phase, where you are trying to improve this neural model, the neural guide for the synthesis process. So what you're doing is you are pulling up some of the tasks that you have. So you're starting with, again, a corpus of tasks. So you're pulling up some of the tasks that you have, and you're seeing, what kind of programs tend to solve these tasks well, and you're using that to improve the neural model. Also, actually, you are taking the current library and you are using that as well as an input to this process. But the bottom line is that you are improving the neural model using the program and the task. So why do we need to do this process over and over again? Well, because the library is changing over time. And so the kinds of programs that you can write are also going to change. And so you need to update your neural guide for the synthesis process. And then the last phase is where some of the symbolic ideas really come to play. So here you're doing this abstraction. So what you're doing is that you are starting with some programs, and then you are refactoring them, you are rewriting them into nearby programs, and you are generating a very, very large space of such programs and storing them in this compact data structure, which is a version space. And then out of that, you're extracting these common sub-expressions and turning them into new routines. And so here's an example up there. So you have one program for task one. So this tree structure basically is the expression tree for the program. So here you have, at the top level, you have a plus, and there is a car, and there is a car is you're pulling up the head of the list, and so on. And then the other one is just doing a cons on a list. And so then you have these two expression trees. But what we note is that there is that orange subtree that is common to both of these things. And so this new library routine is going to be, in this case, extracted from these two programs. And you're going to have this orange subtree basically taken out, and it's going to be put into the library as a new module. And again, for more details, please see the paper. Any questions about this? Yeah? If what, sorry? Right, so there is the potential for this to take a lot of time, because ultimately there is a combinatorial space here, but there are ways in which you can control the search space. So for one, you restrict the, oh, you're talking about the wake phase, not the abstraction phase. Yeah, so go ahead.
Yeah, maybe I can answer that. So this whole process, the working of this whole process is very dependent on having a powerful enough synthesis engine, underlying synthesis engine. And so, because especially in the first step, you are trying to synthesize some of these programs from a very, very low level language. And so you need to have a synthesizer that out of the box is powerful enough to actually find solutions to at least some of the easier programs within this corpus. It's also important that the corpus contains a broad range of programs of complexity.
Yeah.
Programs of different complexity. If your corpus is just all really hard programs, then this is not going to work. Or if you have really big gaps in the complexity where there's a bunch of easy programs and then super hard problems, then you're going to need a really powerful synthesizer to bridge that gap.
Yeah, you can think of this as a curriculum, right? So you're starting with some initial tasks that are easy, and then as you're going up in the curriculum, you're doing harder and harder tasks. That will probably be a way of mitigating this issue.
Although an important thing to note is that unlike traditional curriculum learning, it doesn't have to be ordered. You don't have to present it in order. You can run all of them in parallel.
Yeah.
Is there some normalization where you print it to normal form after you add something new to the library, where you reduce the lab expression into some uniform. This kind of reminds me of Montana's flow reactor in lambda calculus. They have some similar construction, but they also reduce it to normal form.
So maybe I can answer that more abstractly. So I think that would be that would be a good thing to do. And I don't think that will cause any problems here. So you can definitely convert it into a normal form in order to avoid generating the same library procedure in various different surface forms again and again.
Okay.
Yeah.
That said, one of the big things about the abstraction process is precisely the fact that because it's considering refactorings, it is able to deal with variability within the programs that still identify some of these common subprotocols.
Thank you.
Anything else? Okay, so moving on, I just want to talk very briefly about one aspect of the neurosymbolic programming problem statement that we have so far ignored, which is the auxiliary constraints on the kinds of programs that we generate. So in particular, when we introduced the picture of neurosymbolic programming, we mentioned that there could be potentially this third input to the learner, which is additional constraints, and these constraints could be, for example, invariance or reachability properties or robustness properties, and in full generality, temporal logic properties. So what I'll show you very briefly now is just how you could possibly imagine incorporating these kinds of additional constraints into the learning process. And so the idea, so one way in which you could go about this is that you could first learn a model using your neurosymbolic methods that you have seen so far. And then after that, you could do a checking of the constraint. But the issue there is that if you're asserting a property, right? So if you're saying that, let's say the model needs to be robust, right? Or avoid some set of bad states. If you're asserting those properties after the fact, it's unlikely that they're going to be satisfied, right? Why would the learner converge to a property that satisfies something like that? So the alternative is to do certified construction. So basically, as you are learning, you incorporate the assertion, the property into the learning process. And in fact, in the ideal setting, you would even come up with a proof that this property is satisfied. Now, one example of this is here. So you have, here you have a very basic neurosymbolic program, which is a controller for a thermostat combined with the model of the environment. So here what you see is that the thermostat has these two modes, on or off, and it's just a discrete switch. So at some point it is in the cooling mode, and in some point, at some point it is in it goes to the warming mode, and then it can switch back as well. Now, let's say that we want to assert this property that we are not going to ever have an extreme temperature. So that is our correctness requirement. Then the question is, how do you actually do learning while keeping that, exposing the learner to that correctness property? So you can do this in a variety of ways. So for example, you could imagine, just sampling a whole bunch of inputs and then penalizing whenever you are violating that assertion. So you could do that. But what I'll show you is something slightly more sophisticated, where you are actually using some of these ideas from formal methods, just because one of the themes of this summer school is how can ideas from formal methods and machine learning come together. And by the way, so in this model, so these two are neural networks, right? And the rest of it is symbolic, and that's why this is a neurosymbolic program. And also you have a data set of trajectories. So there is a quantitative loss function as well. So basically you're trying to create a behavior, or you're trying to learn parameters that can reproduce the trajectories that you are seeing over there, but also satisfy the safety assertions that are there in this program. Okay, So then you can pose this problem as a constrained optimization problem. So you are trying to find parameters theta such that this trajectory data set is being properly fit. And so you have a signal Q of theta that is capturing this. But then you also have a constraint, which is this safety signal, C of theta, and we want that to be less than or equal to 0. Right? So if you have a Boolean constraint, you could convert that into a quantitative form like this. So then it turns out that you can take this kind of a constraint optimization problem and relax it into this sort of an unconstrained problem where there is a penalty lambda given for high values of that C of theta, which basically means that you are going more towards violating the constraint. And there is a reduction here that shows that the constraint problem above is the same as a somewhat more complex version of this unconstrained problem below. So there is basically a loop over lambda as well that you need to have, but we'll ignore that aspect for now. So then the question is, how do you actually come up with gradients for this kind of a thing? Because the C is about correctness proofs of programs, which now include neural modules as well. So how do you turn it into a differentiable signal? And so the idea that we used in this work is that you basically execute the program on a set of states simultaneously, but the set of states is represented using a symbolic representation. So for example, you can think of intervals as a basic version of this, but you could also more generally have polytopes and ellipses and so on and so forth. So now there are all these methods in the programming languages community for propagating these sorts of symbolic inputs through programs. And this one particular strategy called symbolic execution, this is very well established in say, software verification. And so you are, what you're doing is that you are sampling parts of this program, and this tree basically represents the control flow of the program. So when there is a node that has 2 children, that means that that's a branch. That's an if then else where you have 2 possible ways to go. And now because you're executing the program on a set of states, you cannot say that I'm only going to take one path. You could go along both paths. So you have to take both into account. And so in the symbolic execution, you have a method for pushing these sorts of symbolic regions, let's say intervals for concreteness, down individual paths. And then what we could do is that we could come up with an aggregate measure that looks at the safety signals that you get for each of these paths. So again, how do you get a safety signal? Well, if you know what the set of all states is along each path, you can basically now take the difference between that and the set of bad states, right? And then you can start quantifying, how bad is that path, on what fraction of the inputs would things go wrong. And then you can aggregate that into this signal C. And it turns out that you have to do some approximations because there is this issue of non-differentiability of discrete branches. But we have a probabilistic method for getting around that issue. Basically, we have, we assign a probability weight to each of these paths. And then what that leads to is that the overall safety signal can be approximated by this expectation, which you see on the bottom right. And then it turns out that you can use stochastic gradient estimators to come up with an approximate gradient for that. And that was fast, but I just wanted to show you these slides. I won't go into any of the experimental results or anything. If you have more questions, Chenshi is actually here. You can talk to her, and I'll be also happy to say more about this. So just going back to the top level. So what we have been trying to convince you about in this tutorial is that there is this very rich space of neurosymbolic programming that is emerging, and you have this bridge possible between symbolic programs, which have these advantages of being interpretable, verifiable, using structured domain knowledge, data efficiency, and then on the other hand, neural networks, which have scalable algorithms, which are flexible, handle messy data, And there is also this growing literature, and this has come up again and again in this tutorial as well as the rest of the summer school, of learning neurosymbolic programs where you're bringing together these discrete symbolic search-based techniques with the statistical techniques from machine learning. And as we said in the first session, this is not a new idea. This has been around since the 1980s. But this is a good time to push on it because there are a lot of innovations that have happened on the formal method side, and of course also on the deep learning side, and we can now bring these ideas together. We have already seen examples of how ideas like symbolic version space representations can come together with neural guided search. We have seen ideas of neural relaxations, which are just a version of this idea of continuous relaxations that's been well used in the optimization community, how that's being used to do program synthesis. So there are all these algorithmic ideas. There's a lot of potential for interplay, and I hope that we convinced you that this is worth exploring. And also, we have a lot of new applications now. This is, again, something we have emphasized again and again. So we saw in the amazing talk by Katie earlier that there are these problems, some of the most fundamental problems about the universe. There is a potential of using some of these ideas of symbolic models together with statistical learning to address some of those. And we have also seen other applications of this sort. So there's a lot of demand by domain experts and science applications. For us, really, at this point, the problem is that we have too many problems and not enough people and not enough methods. So yeah, and with that, we'll end the lecture part of this tutorial, and we'll move on to the hands-on activity of today. And Jennifer will tell you more about what today's tasks are. And by the way, if you have questions about the last part, we don't want to take away time from the tutorial, the hands-on activity, but please come up here and ask us. We'll be here.
Thanks, Swarat. Yeah, so for today, the hands-on activity. Oh, it is my is on. Can you turn yourself? Oh, thanks. Oh, yeah, so the hands-on activity today will be based on the same data set that you have been working on for the past few days. One special thing to note today is that this session is your last chance to submit to the summer school challenge. So we've provided some additional instructions in the notebook today, and you have a little bit of extra time today. So make sure you submit and have a chance at the summer school prizes. For the code structure, we start off by running near, which is an algorithm that Yisong and Swarat have talked about for the past few days, with using both a base DSL as well as a more filtered DSL. Running near, it looks really similar to enumeration that you have run for the past yesterday, except there's a lot more hyperparameters. So in the notebook itself, we describe what each of these hyperparameters do, and also raise your hand if you have questions. Another thing that we have similar to before is we have codes for visualizing runtime and classification performance so that you can add your near runs and your enumeration runs all together and compare the runtime and F1 score of both algorithms. In the last part of the tutorial, since there is a lot of different ways that things can go, we have a choose your own path type of thing happening. So the first thing is an open exploration with a lot of suggestions, and you can modify these algorithms. For the next part, you can choose to modify the heuristic architecture. So we provide to you a 2-layer neural network, but you can modify it to be 1 layer or 3 layers in the instructions. We also have an option to use iterative deepening depth first search instead of A* search for doing using near. And the last part is that you could test on other behaviors. So previously, you've worked mostly on investigation labels, but we provide to you as well as mount labels so that you can test how well your DSL and the algorithm generalizes to these other behavior classes. For some potential areas to explore, the simplest thing perhaps to do is to look at the effect of different search hyperparameters on the algorithm. You can also modify the DSL file, which contains the DSLs that you can use for the search. And finally, in your .ipython notebook, you can modify the search algorithms themselves. So with this, I'll try to give you guys some extra time to get started on the 30-minute walkthrough. Again, similar to the past few days, raise your hand if you have questions, and we really encourage you guys to work in groups. The challenge does take teams of up to 3, so feel free to submit in your group at any time. And with that, I'll let you guys get started. Thanks.